We are really a technology program, and we're really building the interconnections on how to connect a digital twin and the interconnectedness of the mini models. If you go to the next one, I'm just going to show you hopefully this visualization. This is just an example of all of the data we have for precipitation, and that's a video. It may or may not work. But a lot of people ask, well, what's NASA? Why is NASA concerned about Earth system digital twins? And oh, if you could go back. But we have more than 24 instruments in space collecting information. But there's such an urgency to understand all of what's happening. We can have a lot of data, but unless we can collect those in inferences and understand what it means and connect our precipitation to our soil, to our agriculture, to what's happening in the atmosphere. It's that interconnectedness that is really the important component of getting to understanding. So you can go to the next one. And I took this picture from ESA. And just again, when we talk about digital twins, it's more than just we have a lot of data. And I know I'm speaking to a community that really understands. We have to understand that in the place, it's place-based understanding, right? So understanding how something is affecting us from across the globe in our local community. So we can collect the satellite data, we can collect the in situ data, but until we can really bring it together in modeling and to analyze it so we can predict what's going to happen now, and then visualize that for others so we can help make those decisions. And again, continue that. I like this visualization because of that infinity loop there, right? And we can go back and collect more information to really get to that understanding. Okay, so here's a picture. And a lot of folks, and I want to start today with, and I think we're going to hear a lot more from our other speakers, of what do we mean by a digital twin? And again, from a technology perspective, what are we doing from the technology perspective to make this happen? So I started my career as a maintenance pilot for aircraft, right? And so in aircraft, I could understand, I knew exactly how each component was going to work. I knew every engine, I knew every generator, I knew the transmission, I knew each coupling, I knew how it was going to work. And as soon as I flew it off, after major maintenance, it worked, exquisitely. Just like when you drive your car off the dealer's lot, brand new, you know exactly what's going to happen. But if you can do one more click, but nobody drives it in all the same conditions every day, right? It could be something's going to happen. And as you go through those different conditions, as you change your environmental conditions, your temperature, pressure, your altitude, right? That's going to change how that aircraft performs. You start going into a very dusty condition, that's going to affect your engine. But that has trickle down effects. And we don't know that unless we can measure those and observe those and bring that into our system understanding. So you have your original aircraft, we know exactly how it's going to work, but then all of a sudden conditions change, right? And you have to understand that, well, what does that mean for the rest of my system? And then if you want to go to one more click here, if you want to really get to the digital twin, you have to understand those human factors, right? There's always somebody out there who's going to do something that you say, I didn't expect that one, right? So how do we understand that? How do you bring that into the Earth system? And we're doing this. So this is just an example of what is the digital twin. You've got your exquisite system, right? You've got that, we now need to bring in our environmental conditions and these changing conditions. And then we have to take into account the human system. And how do you continuously update and continuously understand what's going to happen next? So I think two more clicks. Sorry for the builds in here. So bringing that kind of idea to the Earth system, Earth science digital twin, really want to talk about components. So this is what we're referring to from a digital twin perspective, so we can get to the technology that's needed to really understand. So we have our digital replica, our what now, and that is just as it says, what right at this moment. It doesn't mean 10 years ago, because our system 10 years ago is quite different, right? So it's bringing in continuous information, our what now, our digital replica. But then we want to understand, well, what's going to happen in 2 days or in 10 years? And how can we bring in these predictions and really our interconnectedness, right? Like, I know that if the temperature rises, there's going to be multiple trickle down effects, so second, third order effects. How can we start forecasting that? And a lot of that we're doing already, right? But that third component is the what if, those impact assessments. well, what if we've got that one person out there that's really going to change things that we don't understand? And that's what we really want to get to. We want to understand how cloud brightening is going to affect our oceans, our atmospheres, and in our crops, right? So, one thing may be happening in one side of the world, but could have a significant impact on the other side of the world. And those are those interconnected components that we want to understand before we start making significant changes. What does that really mean? And this can be done at multiple scales. So this is whether we're looking at how it's going to affect, small components at the city scale or at the global scale. Could it be at the daily to weekly scale or the climate change scale? So we're really looking at that. And so some of the components from a technology perspective that we're really driving to are, again, those continuous observations, how to bring those in a smart way. We know computational assets are at a premium, right? So what's the smart way to bring in continuous observations? From multiple sources, again, the interconnected models. How do we do that? We can't, manually couple each model. That's not going to get us to the point of the urgency we have with the climate crisis, right? So how can we do that in a smarter way through surrogate models or others? Many scales. So I'm just going down the list here. And the last one on there I want to point out there is causality. We want to understand what's causing this, and being able to be a fully interconnected system, we can understand some of that causality and uncertainty. All right, next slide. So this really leads into and is a big component of NASA's Earth Science Division new strategy. And this just came out at the beginning of the calendar year. And this is our Earth Science to Action strategy. And we really are, again, recognizing that urgency that we have this information, whether it's NASA, whether it's interagency, whether it's international. A lot of the information and the data exists, but it's not until we can bring it together, visualize it, share it, analyze it, and then go back and get more that we can really make some change. So 2 objectives: holistically observe, monitor, and understand, and 2, deliver trusted information to drive Earth resilience activities. So if we can better inform those decisions that are being made, we can, again, drive resilience. Next slide. So what are we doing, right? That was a big lead into some of the technology projects that we have going. So I'm just going to share a couple of them, and hopefully we can talk more about them in the discussion. No, so next. And so we have quite a few that are really looking at the research and development behind the foundation models. So not the actual implementation, but what can we really do to better use those? So looking at using vision transformers, and then in the last talk we just heard a lot about it, that semi-supervised learning. So how can we use coupled statistics, physics guided learning, and then how can we use, what is the new technology that we really need to get to be able to implement these in a rapid format? So large language models, those are out there. How do we use them for the large data that Earth and our satellites are retrieving? Next. Yeah, I mentioned surrogate models earlier, and how do we do some of these this coupled modeling at large scale, right? So we've got a project, and I want to acknowledge here that this is all funded work. So these are at various universities across NASA centers, across other agencies, and this is just work that's being done through the EISD program. So we've got coupled reusable Earth system tensor framework. Yep, go ahead. Okay. Sorry, I thought there was a question in there. And yeah, so there goes that. And then we're doing a couple prototyping activities. So one that we're really looking at is agriculture. And those from George Mason here may recognize crop chasma. But how can we better get to some of the crop yields? Agriculture is obviously a huge component in what the Earth system is looking at. And I think I'm running out of time, so I'll just kind of rush through this. But yeah, how can we better couple many of the models that we already have through surrogate modeling or other technologies? Next. And the other big one that we're leading up to is the Coastal Zone Digital Twin. This is a partnership between NASA, NOAA, and CNES. Obviously, there is a lot of data, and there's a lot of urgency and concern around the coastal zone. as we look at sea level rise and the impact of saltwater intrusion, at the impacts of human migration and having to move due to rising sea levels. So we're really looking at, again, not just the effects of sea level rise, but those second, third, fourth order impacts, and how can we bring the information together to get to the impact assessments necessary for better decisions. And again, I think I'm out of time due to the kind of slow start there. So I think the last slide is just some of our reference documents that we have out there. Again, as a technology research component, we are really trying to lead what's really going to be needed in the next five-year time frame. So this is a workshop report that we completed back in 22 on some of the technologies needed for digital twins, as well as an architecture framework report that we put together. So we're really looking at not the individual digital twins, but the framework that will be needed to make these more available in the future. So I will stop there. I'm sure, hopefully there's a lot of questions. I know I rushed through it, but I'm looking forward to hearing from the other speakers so that we can have a full discussion moving forward. So thank you.
Thank you, Laura.
Introduction of Dr. Xingyue Ye. Dr. Ye is a Held Adams Indoor Professor in Urban Informatics at Texas A&M University. His current research is centered on urban digital twin and precision public health, emphasizing real-time 3D modeling and AI-enabled participatory planning, as well as urban climate science, with a focus on downscaling climate data to the built environment skills and its relevance to human mobility. Dr. Ye is ranked as the second in urban analytics, sixth in spatial data science based on his publication. He is also among the world's top 2% scientists by the data from Stanford University. Very honored to have you here, Dr. Ye.
Thank you. Thank you, everyone. Thank you for having me here. So let me share my screen. This one. Sure. Can you see my screen?
Yeah, seems like it starts sharing. Should be ready in a second. Yes, we can see your share screen.
Okay. Let me do something. Yeah, I make full screen. Okay. Thank you. So what I will report today is for the National Academies workshop, because I serve as a kind of a national committee member for digital twin research, and we organize kind of a digital twin for atmospheric and climate sciences last year, and the report is free for download online, so you can use a QR code. So I will summarize what we found, and probably since it's very much relevant what has been reported by NASA's talk. So first is you might wonder why we have a digital twin committee again from the National Academies. Like about 12 years ago, the digital twin term was coined to define how we make physical models for using the integrated multi-physics, multi-skill, and kind of simulation, and use it to mimic the real world. And in our report, very much we define digital twin to emphasize the importance of context. Behavior is not only a natural system, but it's also an engineered and social system. Now, for that, the bidirectional interaction between the virtual and the physical is essential to the digital twin. Now, for that, we are not only looking to the data-driven digital twin, we are also looking to the model kind of the driven, because if you do not have enough data, we can use a model to data. So we invite quite a few expert scholars into the workshop. So I try to summarize our kind of outcomes. And certainly, yesterday the European Union's destination Earth from Mike's talk. So that's a big, ambitious work try to simulate and replicate the Earth's digital twin. At the same time, we did that we were looking to how the climate modeling and how it toward especially more traceable and model hierarchies. So we will emphasize the actual skill system for the computing. So in the building a highly accurate digital twin of the Earth, it's still in its first phase of a 7 to 10 year initiative. The data handling is huge, is managed up to 1 PB of data per day. Try to simulate 1 to 4 km resolution. The big challenge is still need to coordinate across infrastructure and build international collaboration. At the same time, the climate model itself now is moved from the 1967 one-dimensional model to modern general circulation models. And the resolution computing computation has a big demand there. However, behind that, we recognize the uncertainty issues. So to deal with these all big models and especially model hierarchies, the actual skilled resources are needed, and the cloud resolving models to promote this kind of solution, especially the large amounts of use. So we also invite quite a few scholars talking about what the current good practices of the digital twin. So apparently one of the use in urban energy optimization, how we can, using digital twin, allow us to estimate energy use at the building level. And using that is not only for looking to building, because the interactions of the city system with human mobility, allowing us to look into the real-time optimization of the urban energy digital twin. At the same time, we need the advancements of digital twins. We need the high resolution climate system procedures especially the advances in machine learning and AI to enhance the traditional modeling capacity. The community already recognize that the current weather model have reached their mesoscale limits. So we need to choose appropriate spatial and temporal skills for digital twin for the climate kind of the modeling. So if you look at the kind of the horizontal and temporal skills and phenomena, you will see the fast growth of the climate models from 1960 to the past decades. There's so many models increasing complexity. So both data and models are there, and very much many of them actually disconnected. So the choosing the right digital twin tools for specific climate research questions are very evident and increasingly important. So we also emphasize the need of the communication channel between the physical and the digital representation and their usefulness for climate research. So beyond the traditional modeling, we also need to leverage many untapped data streams. The digital twin is not only about predict the future, it's about yesterday, tomorrow. So there are many yesterdays the data has not been put into the data yet. So how we leverage many untapped data streams for the enhanced climate model is a big question. And even the high resolution does not necessarily mean more accurate predictions. So there's many systematic and bias or missing procedures that need to be taken into consideration. Regarding the technical challenges and opportunities, so we realize SILP, or we want to call it very accurate Earth digital twins for climate relation infeasible. So behind that, we need more theories, advanced computing and machine learning driven collaboration for improvements. And the digital twin will still face challenges in credibility. And we don't have enough specialists on that. And since you create a digital twin, we need to think about the long-term stability, the real-time operation decision making. So again, the physical engineering system and Earth system should have interconnected the digital twin to accurately reflect their behavior and optimize operations for sustainability. Someone even a group of scholars even argue is if we keep it twin, it might be misleading because it's really impossible for us to replicate the Earth's complexity. So replicate the Earth's complexity might be impossible, but harness the Earth's complexity is possible. Last but not least, we have the including Dr. Goodchild. We have a follow-up discussion about the transparency, societal benefit, and equity in digital twin. All the scholars emphasize we need to have the put a human in the central for digital twin, because digital twin is very much we use for decision making. With this was decision making, then we need the human dimension. We also need the proper education for the use of digital twin. And regarding the societal benefits and ethical considerations, since it will be used for decision making, the location privacy, and also the special location privacy, certainly modeling and even data sharing agreements emerging issues for the digital twins. And the last but not least is building confidence and diverse kind of a community. Because digital twin is a new thing to many local communities and federal agencies. So there's things we have bias. So the co-development with diverse end users are very important. And so I will stop here and take questions later. Thank you.
Yeah, thank you, Dr. Ye. We'll hold the question until the end to have the discussion.
And now let's move to our next panel presenter, Dr. Piero Govacci. Dr. Govacci is a chef scientist at BioMediWare, which is a company and also research leader in the space-time analysis of real-world dynamic systems. Before joining BioMediWare, he was a faculty at the University of Michigan, as well as the University of Florida. Dr. Govacci has authored more than 160 papers in the field of serological and applied geostatistics. He's also a consultant on environmental projects dealing with the characterization of air, soil, and water pollution and its impact on human health. Dr. Govacci, the floor is yours.
Thank you. Well, actually, I'm calling you from the room of a hotel in Arlington. So, but my background is actually I live on a lake in Michigan. So I'm going to shift gear. I'm not going to talk about digital twins. I mean, the only thing I can offer is that I'm a twin myself, and my mother is a twin. But it's all I can tell about twins. But I was asked to talk a little bit about my experience actually working for a small business in the area of space-time data visualizations, and I've been working with BioMediWare for the last 22 years, developing software. And so, as it was mentioned, actually, I wear many hats, which make things interesting. I used to be actually on the University of Florida, University of Michigan, and also University of Florida. So I was part of the, ivory tower of academia. Then I've been part of BioMediWare, which is a small research and development company for the last 22 years. This was, the team when we had bigger companies. We had to downsize following COVID, but and then I had my own consulting companies, and I've been doing consulting and working on real case studies and real world problems. And I was an expert witness for Deepwater Horizon oil spill. I was also an expert witness on the Flint drinking water crisis. So there you are working with engineers, we are working with lawyers. There are specific questions to answer, and actually it's an interesting world because they want something that's actually easy to explain. So they don't want something too sophisticated. And in particular, when you work with lawyers, they don't like the concept of uncertainty, because if you have to present that to the judge and then you start talking about uncertainty, it means that you are not really certain about what you are presenting. So it has been a very interesting journey. And feeling, I think, at some point maybe more useful and more part of the real world than just attending conferences and publishing. Also, it's important. So yeah, I'm trying not to get you sleep. In terms of working for BioMedware, all the funding, I've been fully funded by NIH for the last 22 years, mainly by NIH. First by the National Cancer Institute, then by the National Institute of Environmental Health, and more recently, actually, by the National Library of Medicine, which actually been funding a lot of recent work on artificial intelligence. And actually, if you look at the NIH website for the different institutes, they have a list of topics of interest for them, and actually for every single institute, one of the topic relates to artificial intelligence. So it's really getting there. They really recognize the importance of this new field. Now, when you have SBIR, what it means first, you don't compete with university. Every institute, NSF and so on, they have a fixed percentage of the budget. I think is around 6% that is only devoted to small businesses. And then you have another funding mechanism that's called STTR, where there is actually a collaboration, a more formal collaboration between universities and small businesses. But in my case, in every proposal, I always try to have on board some consultant and some people from academia. Now, when you have a SBIR, that means that the company must develop a product. And the product in this case is a software. And also, and not only we develop the software, but I think what is very important is to do the teaching, the outreach. And since I left the university, I've been actually teaching many more people, more than 1,000 people around the world. I've been teaching on every single continent except Antarctica. I don't think there's a lot of opportunities over there, but I've been teaching in India. I've been teaching in China. I had some in-house short courses in France, teaching in Africa, Colombia, South Korea. And so that's very interesting to interact with people and see what are the needs. And I think training is a very important component of what I do. And then I still do also some coding. And then the consulting, I mean, one of my current project is the dredging of the Kalamazoo rivers. And, and what is very interesting is then you realize there is such a big gap between what is being developed in academia and what is being used in the real world. I mean, there are still models, right, these days that are being developed using inverse square distance. So don't try to talk to them about kriging. It's already advanced. And if you start talking about stochastic simulation, and then you start talking about artificial intelligence, these people would be lost. So there's a lot of work, and I think it was mentioned in the last few days, trying to bridge the gap between what we do in academia and what is happening in the real world, in particular if we are concerned about having an impact outside academia. So I would like to talk a little bit about BioMedware. I don't want to do much publicity, but actually some of the tools we have developed are actually free of charge. So, we're not sending anything there. And the way the company started, when I joined the company, we had just a big project with the National Cancer Institute. As some of you may know, they have an atlas of cancer data. So they have maps of cancer mortality at the county level for different years, for different genders, ethnic groups. And at the time, they had just paper maps, big books of an atlas. And what we developed is a Cancer Atlas Viewer. So we thought, okay, we have this project and we download the data from NCI and start doing some visualizations, mapping, animation in space and time, do queries, and basic graph like scatter plot, histogram, and so on. And then when I joined the company, we thought, okay, well, people might be interested in uploading their own data sets and doing, their analysis. And so we started developing this tool called SpaceStat. At the time, there was some collaboration, very brief, with Luc Anselin. And then what I did is start implementing more and more statistical techniques. So not just do visualizations, but do analysis like cluster detection, all the tools in terms of geostatistics, spatial interpolation, space-time interpolation, principal component analysis. And so we had different software, not only SpaceStat, ClusterSeer, BoundarySeer. And what we realized what actually very popular at the time is actually to develop an advisor, because a lot of time, in particular, if you want to do cluster detection, there are many, many different techniques, and people might be lost and trying to, pick up the right technique. So we were asking people a series of questions and trying to get them to the correct test, if you want. And I think this is where artificial intelligence could help this type of, advisor to help and try to guide the person. Recently, I saw a conference, there was a workshop, and they were trying even beyond. It's like AI could just look at your data. There is a library of previous analysis of data sets, and based on the data, based on the question you are trying to answer, they would actually conduct the analysis for you, and then there was a lot of statisticians in the rooms, students who were actually getting concerned about, am I going to still have a job? And I don't think we're there yet. When we talk about AI, I like the concept of augmented intelligence instead of artificial intelligence. I think it's a tool that you can use, it can help you to be more efficient, but I don't think it's going to replace you or replace, analysts. What we do too also that may be interesting, we have a series of blogs, and on different topics, there is what is geostatistics, so there are blogs about AI. What we're going to do starting next week is to develop podcasts between me and Geoffrey Jacquet, who is the president of the company, and kind of have some discussion between the two of us about different topics, about how did we end up, getting interested in spatial statistics. What do we do when we get a data set? What's the first steps? And so we thought that instead of having, formal lectures, having this kind of podcast and interactions between two veterans in the field might be interested. So you might be, you may want to sign up and hear about us, and we also have a LinkedIn page. And I was talking about SpaceStat, so that's free of charge. We used to sell it, but no longer. So if you're interested, it's a way to visualize the data compared to other tools. And I know a lot of people use ArcGIS. It has less functionalities, so actually it's much more user-friendly. And it's why every time I was teaching, I would use the tool, because I had a 5-day short course on geostatistics. As I was mentioning, I'm not teaching a software, I'm teaching a set of techniques, but I want people to be able to experience and get used to some of these tools. And SpaceStat has a very, doesn't have a steep learning curve. So you can very easily, within a few minutes, import your data, which actually, when you talk to people, is sometimes the most difficult part of the process for the people in the real world, is to get the data inside the software and then just create the maps. And so we also have a series of tutorials, again, as I was mentioning before, the importance of doing some training, and some of the interface. Don't want to go into the details, but and then we have a user manual, which is also very interesting. When you work for small businesses, you spend a lot of time working on the help menu, And then you realize that most people, they don't actually want to use or to look at the help menu. They want to start using the software. So you spend a lot of time, working, putting all your knowledge into this type of document, knowing that most people don't even want to look at that, but we start asking questions when they cannot figure out how to use it. And it's also the interesting part when you start developing this type of tools is that you want to make it very user-friendly. And because you want, again, to broaden the use of these tools. So you want to extend beyond the academic communities. And again, sometimes when I submit proposals, it's being reviewed by academics. So they will tell me, oh, there's all these R functionalities, there's all these free functions out there. And I say, yeah, but people in public health department, people in real world, they don't use R. They don't want to have to start coding or even, linking things like I've seen. They want to click on something very user-friendly. Also, when you start working with public health department, you have to understand that there's a confidentiality issues. So when we start telling people, oh, we can have a cloud-based versions, you just upload your data in the cloud, they don't want that. A lot of the time they have kind of barriers, or they don't even want the computer to be connected to the internet, again, for confidentiality issues. So this needs to be kept in mind. And then this is a new tool we've been working on called Vesta. This one, we were trying again to do something more user-friendly, and like people can create map with a satellite imagery as a background. And so that's where we're trying to go and trend. We had some recent project on joint point regressions, which is being used by NIH to model temporal trends, but we developed a spatial version of joint point regressions. We've been working on multivariate geostatistics, co-kriging, and I just got a big grant funded to work on modeling uncertainty using indicator kriging and compositional kriging. So when the variables add up to a constant. My last proposal actually was not funded, but it was on GeoAI, so it's still a new topic. And actually is the reason also I'm attending this conference to do some networking and see what we can develop in this case. And again, these are some of the tools that are being developed. And again, we always welcome any feedback. And I'm going to end it here. And I think, let's say, stop sharing my screen.
Thank you so much, Dr. Govach. I think you brought up a very important point, like how can we close the gap between academia and like the real world problems? And we're very excited to learn the products and the tools your company developed and those like real world example. We really appreciate.
Thank you. Welcome.
Thank you.
Our next panelist is Dr. James Kenter from George Mason, my long-term colleague at Mason. And he received his PhD from Princeton and also a member of the National Academy study on digital twins. He is the director of Virginia Climate Center and also the director of the Center for Ocean and Atmosphere Studies, COLA, which is one of the organization developed IPCC that received the Nobel Prize. Dr. Kinder, please take away.
Okay, thank you very much, Bill, and thanks for inviting me. Let me see if I can share my screen. Okay, can you see the PowerPoint slide?
Yes.
Okay, let me put it in full screen for you. Okay, well, it's great to be here with you today, and it's also great that I got to follow Dr. Ye because he spoke about one specific portion of this National Academy report that he and I were both part of. And I'm going to give you sort of zoom out and give you a broader view of what this report was all about. The report, you can use the QR code that's on the screen to get to the website where the report is available. This was a report that came out around just before the holidays last year in December. And it looks at foundational research gaps and future directions for a research agenda in the area of digital twins. Let me get this, there we go. The study was actually requested by several federal agencies, and we were asked to address all of these questions that you see on the screen now, including revising the definition, as Dr. Ye just described, looking at what are the foundational research needs, looking at promising practices across domains, and also opportunities for translation of best practices across domains. And that's a very important aspect because, as Dr. Ye was describing, just looking at the earth science bit, the weather and climate portion of the world, this study actually is much broader than that. We had people on the committee, let me go to the next slide, and you can see who was on the committee. We had people from engineering, from medical science, from data science, from earth science, from chemistry. So we had quite a broad range of, it was sort of a blue ribbon panel, myself excluded. It was sort of a blue ribbon panel of people from a number of different disciplines, all of whom have been active in this area of digital twins in the sense of both modeling and two-way data flows. So the first and biggest message has come out from this National Academy report is that there's a lot of potential in applying digital twins for both scientific discovery and for pushing our industrial capabilities forward. So this is really sort of, it was a bit new for me because I've been deeply embedded in just the basic research community. Into practice, and particularly into industrial settings, was quite a novel thing for me, but a very important aspect of this report. Now, as Dr. Ye mentioned, we took some time to revise the definition of what a digital twin is, and you can see all the words on the screen. I'll just emphasize two things. One is that we emphasize this bidirectional flow of information from a physical system to a digital system. And that could be a computer model, it could be a data model. It is a digital representation of a real world object. And the other thing I'll mention is that we emphasize the fact that we want digital twins to have predictive capability and therefore to produce information which has value. Now, an important aspect of this report that we emphasize over and over again is that a digital twin is more than just a simulation or a model of a physical system. It's really this loop of activities. So on the left-hand side of this diagram, you see in the black region, the physical system. So this might be a helicopter engine, such as you saw in Laura's presentation, or it might be the whole planet Earth, or it might be a human body. So the physical counterpart has to be a very well-defined, basically in the way that we usually do in physics, we define what is the system that we're addressing. On the right-hand side of the diagram, you see the virtual representation. This is a digital form that attempts to approximate either the nature or the behavior of the physical counterpart on the left. And then you see these directional arrows where information is flowing from the physical world to the virtual representation, and again, from the virtual representation to the physical world. And then in the middle of the diagram, you see humans. So we also took into account in this report the fact that humans are in the loop, specifically in a number of examples that I'll show you in a second. You also notice around the outside of the diagram, there are these green arrows, and they represent three very important aspects of digital twins that our report also focused on. One is verification, validation, and uncertainty quantification. Verification is demonstrating that a model actually represents the physical system. Validation is that it represents the physical system. Verification is that it actually produces behavior that mimics the physical system. And uncertainty quantification is the one that I think is probably gotten the least attention in the research world, is that we know that there are approximations, we know that there are errors and biases built into our digital representations of anything in the physical, chemical, or biological world, and we need to quantify that uncertainty. Also important in these green arrows are security, and I'll mention how that plays in to one of our examples, and ethics, also very important. So here's an example. This is from the medical science world. Let's see if I can get this out of the way a little bit. There we go. So imagine that we have a cancer patient. That's that human-looking form on the top part of the diagram. And imagine that we also have a digital twin of this cancer patient. That's the blue dotted figure on the bottom. So our virtual representation might be a mechanistic model, it might be an empirical model, it might be looking at blood flow, for example, and thinking about how fluids flow through the containment of blood vessels in the human body. And it might also be a representation of how patients respond to pharmaceuticals, drug therapies, and what have you. The physical counterpart would be based on data collected from the patients. So we have lots and lots of data we now collect from patients, particularly patients who are in extensive care, like cancer patients. We're collecting from scans and from blood tests. So we have chemistry and biology and physical characteristics of the human body. The interaction between these two is where we gather data from the human subject, the patient, and we use that to update the equations or the data sets that we use in the digital representation. Similarly, the data flowing from the digital representation might inform clinical decisions, maybe try a different drug therapy, a different chemotherapy that would be recommended because the patient has reacted in a certain way to a previous regimen. So this is where you can see that both security and ethics play a very big role as we start to think about creating a digital twin of individual humans. We need to protect those humans' private information, and we need to be ethical about the way that we use the digital information that we gather from our human patients. Here's another example. This is from the earth sciences, and particularly very near and dear to my heart is looking at numerical weather prediction. So when we're thinking about a hurricane, we have a digital representation, which is a numerical weather prediction model. And I put a supercomputer picture on the screen just to show that this is where those equations get ground, churned forward in time to produce forecasts. The physical counterpart is obvious. It's a storm. You see it looking out the window of a Hurricane Hunter aircraft there in the middle picture. A very large storm, which has tremendous destructive potential, both from wind and flooding. And the bidirectional information is that we gather data. We gather data from a huge variety of sensors. You heard from Laura about the sensors that NASA has deployed for doing Earth system observation, but we also do in situ measurements from very brave individuals who go up in these rickety, well, they're not rickety, but they're what I would certainly never do what hurricane hunters do, and get in an airplane that looks like the picture you see there and fly right into a storm with 150-mile-an-hour winds. But they are doing that, and they're collecting those data, and then those data are used to update the numerical weather prediction model, which in turn is providing information about where to send the next mission. So each Hurricane Hunter mission has a flight path which is devised based on the forecast information. So one of the things that we found in our report about digital twins is that there's been a lot of hype. Digital twins, everybody has a digital twin now, and we have to find a way to prevent that excessive hype from causing lack of trust in the science that we are developing. So if we say that a digital twin can deliver X, Y, and Z, we have to quantify the uncertainty around the predictions that a digital twin makes in order to enhance the trust and strengthen credibility of the system. So this gets to one of the recommendations in the reports about verification, validation, and uncertainty quantification. It has to be embedded in the design and the deployment of all digital twins, and we need new methods. So there's a research opportunity here to find better ways validating and quantifying uncertainty in digital twins. We also think that there should be a parallel development of digital twins, both from data science or from computer science technologies and from the uncertainty quantification side. Another big recommendation for the report, and Dr. Ye alluded to this, is digital twins should be fit for purpose. So particularly thinking about the earth sciences, we have numerical models of the earth system, and the resolution that we use in those models should match the processes we're trying to represent in those models. And we find that this fitness for purpose might be intractable in some cases. So in the case of Destination Earth, the goal is a kilometer scale global Earth system model, which can be used to produce simulations of multiple decades or centuries. And that's just simply beyond the capability of computers using the algorithms that we have today. One of the things that came out of this report is this program, an agenda for future research. And so I'm not going to go through all of these, but just basically thinking about a great many things where there are opportunities for research, and the federal agencies in particular are being exhorted to think about how they can support and accelerate the developments in virtual representation, in acquisition of data from physical counterpart systems, the scalable assimilation of data from the physical world into the digital representation, scalable optimization, and particularly in the presence of uncertainty, as we have certainly in all digital twin exercises. And finally, that human digital twin interface, where we would have to think about user-centered design, ethics, privacy, diversity, and communication as all very important aspects of using digital twins. So that's all I had for today. Be happy to answer questions when we get to the Q&A session.
Thank you, Dr. Kinter. Some of our participants have already posted their questions in the chat box. So for all our panel speakers, please take a look. Our presenters have already answered some of the questions have been posted on the chat box. So if you have additional questions, please feel free to post, or you can just unmute yourself and ask questions directly to our presenter.
Yeah, at the same time, we would invite our panelists to please share your video, and we can see you. We're going to have some discussions. Yeah, as she mentioned, we already have some questions answered by our panelists. So for our participants, please put your question in the chat window. Maybe we can start from the kind of core one. I think all our panelists mentioned about one of the capability skills of digital twin is to be able to simulate or be able to predict. For one of the panels I participated in the past, there's a mention about the engine of digital twins, which basically means that the engine, the thinking or the simulation, the forecasting, the prediction capability. So what is your take on the forecasting capability of digital twins? What is needed to support that?
Well, I'll start. One of the things that we know about the Earth system in particular is that predictability is a big issue. We have predictability limits for weather. So this was demonstrated in the 1960s that weather has a limit of predictability of about 2 weeks, and that number has held up for 6 decades. So when we talk about climate prediction, which is a much longer time scale, everybody asks the question, if you can't predict the weather, how can you predict the climate? And the answer, of course, is that there are other processes that dominate the climate system and the Earth system that have slower time scales. So this kind of gets to the fitness of purpose point in the Academy report, that when we think about prediction, we have to be very careful to make sure that our digital twin or our methodology is appropriate for the system that we're trying to make predictions, and also that we are very careful to quantify the uncertainty So, you know, in the example I showed of the hurricane, we have a cone of uncertainty about the hurricane path. We need that kind of information about basically everything we get from a digital twin.
Regarding Phil's question, I also want to address the previous post by Yano about the unknown, how to address unknown, because it's highly relevant to prediction of digital twin. Because addressing unknown unknowns in digital twins, certainly we need to acknowledge our current the limitation of our current models and data. Because no matter how we put together previous model, data, experience, but we still will miss unexpected events or conditions which is not captured in existing, especially considering we have the increasing frequencies of extreme weather. For example, 2 years ago, Texas has a heavy snow, which have not occurred in many cities for even we haven't seen any snow on the ground, but it occurred. So what we should do? So to deal with that, to enhance this kind of prediction, on one side, we leverage the advances, as Yano mentioned, the geospatial intelligence. But we really need a diverse workforce, help us to bring together a wider range of data and perspectives. The continuous co-learning and updating with new scenarios will improve model accuracy. And for that, the digital twin will call the more needs for international collaboration to considering different value systems. It will enhance our prediction and ethics. Yes, that's what my thoughts.
Thank you, Dr. Ye. Do we have any follow-up from Laura or?
Well, I think it was hit really well. I mean, fitness for purpose. You really need to look at what are you really trying to do, and using the correct models, the correct scale, understanding what you're looking at. Prediction is going to vary widely, and you know the seasonal subseasonal scale is a very different scale than the 10-year scale, which we really struggle in that range, right? So just understanding what you're trying to do, and that's where it's difficult, right? And that's where to try to just say here to the public, use this, if we have to have that really strong understanding of what's being done and how we can share that. And a lot of that is behind the scenes, and it's difficult, but understanding what you're trying to do and understanding your scale.
Yeah, and I would like to, I mean, there were some comments yesterday during the plenary sessions about the fact that a lot of time, and I have experienced that many times as a statistician, people come to you with the data and they ask you, what can I do with the data? And then always your reply is, well, which type of question you want to answer? And then a lot of time they realize that they cannot really answer this question using the data they collected because they don't think about it at the time. So, and also, I think when you try to create models and do predictions, I think there are different order in terms of decisions. And a lot of time people are more concerned about trying to estimate the parameters of the model accurately instead of questioning, okay, is it actually the right model to use? And sometimes there's big assumption like stationarity and so on. They might not be very reliable or very appropriate. But based on that, then, you know, the uncertainty about the parameters itself is important, but sometimes it's not what will have the largest impact on the predictions. Might be the model itself or some of the big assumption you're making. And sometimes you cannot really test. I mean, it's a kind of decision you make. So sometimes I say that's not actually an assumption and a hypothesis because you cannot test it. It's more a decision you make. And it needs to be upfront and say, okay, I'm making this decision that, you know, that and that is true. And then based on that, I start, you know, looking at how to estimate my parameters accurately. But sometimes we're focusing too much about small things, like the accuracy of the parameters instead of the big decision, the big things about the scale of the model, the type of the model, some of the assumptions about stationarity and so on.
Thank you. Our next question, in fact, we can start with Dr. Guvertz. It's about how the spatial temporal data, so that's the theme of our symposium, how the analytics of the spatial temporal data or handling of spatial temporal data sets would contribute into or adding complexities to digital twins. Maybe we can start from you, because there's a related question over there about how the software tools could analyze the data sets for the cities.
Yeah, I'm assuming it was related to space that. Yeah, I mean, we have been working actually with urban design, and actually we developed at some point another piece of software called Metric. And it was actually a contract with the National Cancer Institute and trying to characterize the environment, the built environment, the food environment, and so on. So they were interested in doing that, is trying to develop this matrix. And again, a lot of time, the issue was where are the data, because people might not know what are the different data sets available. And again, the reliability of these data sets. And this may be where some artificial intelligence could help us with that. So we have looked at tools to, to do this modeling of cities. We also actually had another, it actually related to something that was discussed also yesterday by John Wilson. We also had another project where we were mapping heat islands in cities based on, where the vegetation is and so on. So we have been developing some of these tools, and again, trying to incorporate the temporal dimension, because it's going to change over time, and I think remote sensing provides some of the tools for that.
Thank you, Dr. Kenter. Do you want to add something? I know you're handling huge amount of spatial temporal data sets. So how that adds to the digital twin initiative?
Well, I mean, I think the big issue for us is, putting on my hat as Virginia Climate Center, our stakeholders are operating at a very local level. So City of Fairfax, Fairfax County, Martinsville, Virginia, these are all small communities, small spatially, not necessarily small in population. And they have challenges relating to climate change and hazards that are becoming more frequent or more intense as a result of climate change. And they're dying to know what they should be doing about it. In particular, thinking about the adaptation side of climate change, if they're going to be exposed to more frequent flash flood or more intense flash flood, more intense heat or longer duration heat waves, more drought, et cetera, they want that information at a very fine spatial scale, even at the neighborhood scale, when they're thinking about things like investing in urban canopies to protect at-risk populations from excessive heat. So our climate models, our Earth system models, are nowhere near the right scale to do that kind of very high resolution information. And so we have to have some kind of transfer functions that take information we get from the large scale climate models down to the actionable neighborhood scale. And that's just a very fertile area of spatio-temporal data research. Is it just an interpolation problem? I heard Pierre talking about Kriging versus linear interpolation. Well, yeah, that's like, forget about it. That's not going to do the job at all. We have to have much more intelligent ways of delivering information at the neighborhood scale to stakeholders who need that information. And so this is, I would say, one of the primary goals for the next couple of years or maybe decade of transforming our Earth system models into actionable tools at the neighborhood scale.
Thank you, Dr. Kenter. Laura.
I'm sorry, I have to run. I literally have to go the entire other side of campus for a dissertation. So
thank you, Dr. Kenter. I really appreciate your help and participate. Laura, we know that Langley hosts one of the NASA BACs, especially on atmosphere and weather. So that really leads to the action or the Earth action that we could. So what's your take on that? How to utilize that spatial temporal data sets and put them into Earth action?
Yeah, and actually, Jim has hit it really well. I mean, we are doing a lot at the climate scale. At NASA Langley, we do a lot with the radiation budget, right? But how to bring that down. So actually, I'm also in Virginia in Hampton Roads, and in our backyards, it's flooding. And we're having this blue sky flooding, and folks are coming to us asking, like, please let us know at the building scale, like building level, what do we need to do as far as sandbags? I mean, that is a really difficult translation when we're looking at satellite data and down to the building scale. We're looking at climate and understanding our Earth radiation budget and our atmospheres down to how is that going to impact these more intense, more frequent storms. And there is that connection, right? So understanding this data, where we can make those linkages. And again, it's not just the interpolation, but at what scales do we need to understand this? How often do we need to, when we think about the forecasting component and going into the what if of those impact assessments, how often do we need to run those climate level models versus the smaller scale and the more rapid ones? So understanding that tree, that federation of models is really something that we're looking to do. And you mentioned the atmosphere work. And again, we go from the radiation budget climate scale down to, let's think about Tempo. So Tempo just launched, and they are getting hourly information on air quality. So that's hourly at the 3-kilometer scale. So bringing those together is a really difficult but exciting problem, right? Like we can do a lot with this information, but it's how we do it, how we understand where that error is, where that mismatch is, and making the connections between uncertainty and that causality. If we can make those connections, we're going to start making a lot of better informed decisions. We'll have that understanding to inform those decisions, but it's a difficult problem. And I actually hope that there's a lot of feedback here, and how can we work to make these things happen, because the data is there.
Yeah,
but making it bring it together.
Yeah, thank you, Laura. Dr. Ye, we know that you have been dealing with kind of the user side, the urban studies, urban planning. So what's your take on the digital twins may be able to take the spatial temporal data sets produced to aid the decision making or the planning in urban and other areas?
Yes, since I'm also a core faculty in A&M, the Hazard Response and Recovery Center, and I'm located in Texas, so everyone knows Gulf states recently suffered a lot from the hurricanes. So for that is we're not only using digital twin, need to allowing us to continuously check and assess hazard condition for example, linking with climate and meteorology data. But at the same time, we need to evaluate the impact of the populations. So, for example, developing population synthesis at a building level, and also use computer vision, geospatial artificial intelligence to link with the vertical urban structures, allowing us to vividly to understand by building, by street, how population and evacuation routes might be impacted by various disasters and flooding issues. So when we using the spatial temporal data sets, we'll be able to putting together on one side is the physical modeling, the climate modeling, on the other side is the human dynamics, the social system. Last but not least is I think our panelists also mentioned also according to a question posted in the chat, so we need a intuitive, highly interactive interface allowing the public to understand the tangible concepts we try to deliver about the local urban analytics. And for that, we also be able to capture their feedback. It will enforce the co-learning procedure. We need the many unmeasured data sets, but it's very valuable perspectives from local communities, allowing us to build the digital twin and the spatial temporal data science much stronger dealing with real challenges. Thank you.
Well, thank you, Dr. Ye. The next question is about uncertainty, and all of you touched on that. So we want to start from Nora. We love your example about the Air Force, the airplane, and how you put them together. And if anything of them is not functioning well, that may be a problem. So you probably need to go to millimeter kind of accuracy or micrometer. Let's see, from the uncertainty part, how do we quantify that? And especially from the sensor side, how could we quantify the uncertainty? And when it goes to the action side, what kind of uncertainty or confidence level we could provide from digital twins?
I mean, that's a loaded question, right? Like uncertainty is one of the most difficult problems. And Pierre touched on it as well. I think we all touched on it. At the sensor level, we have a good understanding of the uncertainty of the data that we're bringing down. But I will also say that there's a potential for a lot more information that we're getting from our satellite retrievals. And a lot of that we can bring down using quantum annealing, for example. We can reduce the noise in our data, and we can have better uncertainty there. But those are things that we're still getting to, and these are new techniques that aren't trusted. So there's a difference between what uncertainty we're saying versus what people trust, right? But that's at the sensor level. If we go down to the action level, it's a very different perspective. If you talk with the communities, they don't necessarily care where some of this data came from. They want to know, when is it going to hit a 3-meter sea level rise? I want to know this number, and that's all I care about. And it's not necessarily, and we'll look at it and say, well, there's a lot of nuance behind that. The timing is uncertain, and try to explain some of this uncertainty. And they're just looking for a very specific number at a specific date. So the confidence level, I have to say, it depends. It's a loaded question. It depends on that spatial-temporal scale, right? And so how to communicate, how to visualize that, I think is a really key piece to really being, there's a question in the chat earlier about how do we propagate the success of digital twins and allow people to really use them for decision making. And I think it's how we communicate them, how we visualize and share the information that we have, and sharing when we have uncertainty, where we believe the uncertainty is. Unless they can visualize that, it'll be very difficult. But those making decisions don't necessarily care about the uncertainty at the sensor level, right? They want to understand at their decision level. I'll stop there. But lots to talk.
Thank you. Yeah, thank you, Laura. Xingyue, do you have any thoughts on uncertainty?
Yes, regarding uncertainty, I think we talk a lot about it because of limitation of data and model, and also considering why digital twin is so popular these days, not only because of advancements and the computing power. The other thing is we really feel the threat of the extreme weathers. We have many unforeseen things, not only in the social domain and also in physical domain, everything. So that is we on one side we need to have the data validation and high quality data, but we need to continuously learn. It's not only the machine, it's also about ourselves. Continue to learn what other disciplinary domains to understand the complexity, holistic view of the issue. No matter even something we call it sustainable development, it's at the cost of certain communities and certain aspects, but we don't know yet. But we thought for that is we really need more like a kind of the interdisciplinary and the diverse workforce together, continuous co-learning. And last but not least is we need when we use a digital twin, we also need to consider we have the responsibility is considering various sensitivity analysis to make sure is how uncertain the results is if we want to use it for the policy recommendation.
Yeah, thank you.
That's all.
Yeah. Pierre, we do know that you have a very strong background in spatial-temporal statistics. That's almost the perfect starting point for quantified uncertainties. So what's your take on this?
Well, I mean, I would agree with Laura about, communication and visualization of uncertainty. And it's interesting because there's been a lot of work, I think, in the climate change community. I know when, people have a hard time interpreting the concept of probability. Or, I mean, if you look at all these apps, they say, okay, in 3 hours, there's a 51% probability of rain here. I mean, when I see 51%, I say it's not going to rain. But people have a hard time interpreting what it means 51%. And I know that in the climate change community, what they were trying to do is to replace these numbers by words like, highly, highly uncertain, or it's very likely, or very, and then they realize that, different communities, different ethnic groups may interpret these words in different ways. So, but what I like to do, and actually there was a very good paper by Mohan Srivastava a long time ago, using actually the same concept of rain. And the question is not only to communicate uncertainty, but incorporate uncertainty in decision-making. And he had a great example, like somebody is ready to leave his home and he has to decide whether he's going to carry an umbrella with him. And he look at the weather forecast and he say, well, if it rains and I don't have my umbrella, I'm going to get wet. But if I carry my umbrella and it doesn't rain, it's going to be annoying. And so the question is, what is the least, costly or impactful decisions? Would you rather get wet because you're not carrying your umbrella, or would you rather carry your umbrella around and it's not going to rain? So I think it's every time we make a decision, there are consequences. And based on the model of uncertainty and maybe cost function, then you can use that and calculate an expected cost. And then people can make decisions based on an expected cost that combine both the concept of uncertainty, but also the fact that every decision you make have an associated cost. And I think that it's easier because then people can make decisions based, for example, on dollar figures instead of probability.
Yeah. Thank you, Pierre. We know the time is already past, about 3 minutes past, but we want to close with the last question. We have a perfect panel here on the federal agency, industry, and academia. This question is to the heart of most of us online here, education. So what's your take on the opportunities or challenges of workforce? Do you view that we're lacking workforce for digital twins, and what kind of skills do we need?
I mean, that's an excellent question. I would say that the workforce is growing and growing, and it's a growing field, is what I'm saying. And I think as we increase the amount of information, increase our understanding, it's only going to be a draw for more information and more understanding and more who can wrangle the data and really make it into something for decision makers. So we're always looking for workforce. I know. We're looking for those who can support this urgent need.
Thank
ready
you.
for you.
Yeah, Pierre, do you have some insight?
Yeah, I mean
from the
reason
side.
I've been teaching all over the world, it's because what I teach, is not offered in many universities. And also they like the perspective of somebody who works, as a consultant about how to analyze the data. I used to be in academia, and my main frustration was that the emphasis is more on grading and get a good GPA than actually learning something. So that was very frustrating for me because I wanted to be able to push my students and spend more time about learning instead of evaluations. And so, and also there's more and more information, and I know it's very hard to keep track of everything. There's more and more journals, more and more papers. There's a lot of noise out there, and to be able really to extract what is useful, it's getting more and more difficult actually, because we're just overwhelmed with so much information.
Thank you, Pierre. Xingyue, do you have anything to add?
Yes, and I think that's a critical thing to train the next generation workforce for handling the digital twin things. And the digital twin, as we discussed so far, out of the various spatial-temporal data models, and we also need to know how to integrate the knowledge, for example, from the meteorology data sets with, for example, urban socioeconomic data sets. And we also need to develop fine scale data, for example, even at the building level, and how to understand human dynamics. All these need a more specialized kind of the training courses and hands-on experience. Then my other experience is at E&M, we have developed a robust connection with the local communities. So many of our recent ongoing projects is we bring students to the local communities to work with local community members together to develop a full twin, because there's quite a few like now the sensors price drops very dramatically, and it's affordable. And on the other side, we have many open source tools we can leverage, especially like from Python or the other interactive visualization tools, or even gaming engines is also easy to use and teach now. So I think I still think on one side, certainly we need a hardcore skills, but on the other side, we need a raise awareness from the general public and raise awareness from non-STEM majors, and bring them in to bring their critical perspective to help us develop digital twin at the yes.
Well, thank you. That's great presentation and discussions from our panelists. Let's give them a big hand. Thank you.